So this lesson, 5.2, trig ratios for special angles. As you can see, starting off, not much here on our page. So what we have, let's start on the left. We obviously have a square. And then within that square, I've taken a line and I've cut it diagonally, kind of between our two corners. But if we initially look at this as a square, we know that with squares, each square has 4 right angle corners, right? 90, 90, 90, 90. So when I take this and I kind of split it in half diagonally, this 90-degree angle now becomes 45. Same down here, this angle becomes 45. Now what we're going to do is we're going to label our side lengths, and I'm just going to label them as 1. Right, because it's a square, all the sides are the same length, so we could choose it to be anything. For right now, we're just going to leave it as a length of 1 unit. So what we have here, when we take this and we cut it in half, is we have a right angle triangle. So we'll just label this as right angle triangle. So we have our 2 side lengths. I need to find this 3rd side of my right angle, which ends up being the hypotenuse, right? Directly opposite that right angle. So we need to determine the hypotenuse. So to do that, we use Pythagorean theorem. C squared equals a squared plus b squared. This c is what we're trying to find. And we get c equal to root 2. Now we're actually going to leave it like that. I'm not going to change it to a decimal. I'm going to leave that as root 2. Okay, so we have a right angle triangle, 2 angles of 45, side lengths of 1. Again, I just arbitrarily chose 1. People are going to be saying, well, where did that 1 come from? Why is it 1? We're just leaving it as a unit of 1. Okay, it could be anything. I could have made it 10, could have made it 20, could have made it 50. But we're just leaving it as 1 for now. Keeps things easier. What I'm going to do next here is I'm going to find my primary trig ratios. I want sine, cos, and tan of this triangle. So the first thing we'll look at is sine of 45 degrees. Now, it doesn't matter which 45 we use because sine is opposite over hypotenuse. Opposite over hypotenuse. Each angle gives us the same trig ratio, so it doesn't matter which one it is that we use. So regardless of the 45, the opposite is 1, and the hypotenuse is root 2. If we look at cos 45, adjacent, again, the adjacent's the same for each of them, over hypotenuse, so 1 over root 2. And then we have tan 45, opposite over adjacent. Opposite over adjacent, we get 1 over 1, which ends up being 1. Now, one thing, we go back to sine and cos 45. We have that root 2 on the bottom. And the thing with root 2 is that if I take the square root of 2, I naturally end up with a decimal. And I don't want a decimal in the denominator, right? It's not a proper form to have 1 over 1.414. So you really don't want to have a radical in our denominator. It's just not good form. So we have to get rid of that root 2 in our denominator. And what we do is we do something called rationalizing the denominator. And what that means is that you're just going to multiply the top and bottom of that fraction by root 2. Same thing for cos. Multiply the top and bottom by root 2. And then when we multiply across, we get 1 times root 2, which is root 2. Root 2 times root 2 is a square root of 4. Square root of 4 is 2. Same thing for cos 45. We end up with root 2 over 2. So what we're doing here is we're going to rationalize the denominator by multiplying by root 2. Just because we don't want to have a radical in the denominator. The numerator is okay, the denominator is not. Okay, so we found sine 45, root 2 over 2, cos 45, root 2 over 2, and tan 45 is 1. Okay, pretty straightforward, just looking at that right angle triangle. As we move over to the right-hand side, we have another triangle here. And for this one, we're going to treat it as an equilateral triangle. Equilateral meaning all sides and all angles are the same. So again, I'm going to just arbitrarily make my side lengths 2. And there's a reason for that, but we'll get to that in a later lesson. But for now, I mean, it could be anything. I could have used 1, I could have used 5, I could have used 10. I chose 2. And really, the main reason I chose 2 was because what we're going to do here is we're going to slice this equilateral in half. And by doing that, we're going to create a right angle triangle. And because I just labeled my side lengths of 2, again, the reason why I chose 2 is because if I'm splitting this in half, rather than that length being 2, it's now just a length of 1. Okay, so if I had have made each side length 1, this would end up being a half. I don't want to deal with fractions. So making it 2, split it in half, gives me a side length of this right angle triangle of 1. Now the other thing about equilateral triangles is that all the sides are the same length and all the angles are the same length as well. So if you remember, for an equilateral, all of your angles are 60. Except up here, if we're splitting it in half, this angle is going to be 30, and then this one will be 30. So we end up with our right angle triangle. So if we just focus in on this triangle here, 30, 60, 90 degree angles, 1, 2, and I still need to find this side length here for my third side. So again, we're going to use Pythagorean theorem to determine the unknown side length. So again, c squared equals a squared plus b squared. C is 2, right? That's the hypotenuse, directly opposite my right angle. So I have 2 squared equals 1 squared plus b squared. So I get 4 minus 1. And I get that side length to be root 3. Now, this triangle is sometimes referred to as a 30, 60, 90, just because of the angles, right? 30 degrees, 60 degrees, 90 degrees. So sometimes if we're talking about this, you refer to it as a 30, 60, 90. I'm going to do the same thing I did with the square with my right angle triangle over on the left, is I'm going to go through sine, cos, and tan. But the difference here is I have 2 angles. Whereas the other, with the right angle, I only had 45. Here I have 30 and 60, so I have to do it for both. So we're going to look at the sine of 30 degrees. So from 30, opposite over hypotenuse, 1/2. Cos of 30, adjacent over hypotenuse, and tan 30. opposite over adjacent. And again, with a radical on the bottom, we can't have that. So we're going to rationalize it. Multiply it by root 3 over root 3. And we get root 3 over root 3 times root 3 is root 9. Square root of 9 is 3. And we're going to do the same thing with 60. Sine 60, opposite over hypotenuse, root 3 over 2. Again, we don't need to rationalize this because the radical on the top is okay. Cos 60, adjacent over hypotenuse, 1/2. And tan 60, opposite over adjacent, root 3 over 1, which gives us root 3. Okay, so from these two triangles that we're looking at, the right angle and the equilateral, I labeled those and kind of gone through them just to show you where I'm getting these values from. Now, 45 degrees, 30 degrees, and 60, I referred to as special angles. So why are those angles special? What about them makes this special? Well, if we go back to our calculator, making sure it's in degrees again, if I type in the sine of 45, I get this decimal. If you can see that, 0.707106781. Now, what if I do root 2 divided by 2? I get the exact same decimal. Not approximately, not close, but I get the exact same. If I type in the tan of 45, I get 1. Not a surprise. What about tan 30? Again, another decimal, 0.57735. Now if I do root 3 divided by 3, the exact same decimal. So what makes these angles special? They're special because 30 degrees, 45, and 60 are the only angles that give us an exact value. We can take the decimal and we can write it as a fraction or with a radical that gives us the exact same decimal. There's no other angles other than 0, 90, 180, 270, and 360, which we'll talk about later, where you can get the exact perfect value written as a fraction or as a radical. So all of these at 30, 45, and 60, we can write them with exact values. And that's why they're special. Okay? So this first page is just to show you where I got these values from. When we look at the next page, we have our table. So if we flip back to the other page where we got our values from, we know that the sine of 30, we determine that to be 1/2. The sine of 45 is root 2 over 2, and the sine of 60 is root 3 over 2. Cos 30 is root 3 over 2. Cos 45, root 2 over 2. And the cos of 60 is 1/2. Tan, root 3 over 3, 1, and root 3. So this are the values that you need to know. Now, if we were in class, you would need to have that table memorized because these are extremely important values moving forward when it comes to dealing with treating with special angles. So I would say you need to know for a test or for a quiz that the cos of 30 degrees is root 3 over 2, or the tan of 30 is root 3 over 3. Now, as I grab a scrap sheet of paper, I'm going to tell you how it's a little easier to figure this out. So along the top, we'll put sine, cos, tan, 30, 45, and 60. So a good way to remember this is put everything with a denominator of 2. Once you have that, we're going to go 1, 2, 3, 3, 2, 1. And then every numerator gets a root. Now we know that the square root of 1 is 1. So that's why we don't have the root there. Square root of 1 is 1, so it just becomes 1/2. So there's sine and cos, right? 1, 2, 3, 3, 2, 1 for your numerators. So really tan is the only trig ratio that you would have to remember. And you just have to remember root 3 over 3, right? 2 3s for 30 degrees. 1, root 3. And there's your special angles. So rather than just giving you this table and saying, here, remember this, this is what you need to know, memorize it, this first page was to show you how we got those values and where they came from. Okay? So once we have this table, now we can go ahead and answer some questions. Keep in mind that these are exact values. So because they're exact values, you use them when the question asks you to find an exact value. So for question 1, determine the exact value of this. So if I type in sine 45, which we know gives me a decimal, I can't use decimals here because they want the exact value. So what we're going to do is sub in our exact values for those angles. So sine 45 is root 2 over 2. Cos 45, root 2 over 2. Plus sine 30 is 1/2. Cos 30, root 3 over 2. And when it comes to multiplying fractions, remember we multiply across the top, multiply the numerators together, multiply the denominators together. Now I don't have a whole lot of space here, so I'll go over here. Root 2 times root 2 is root 4. Square root of 4 is 2. And then the denominator 2 times 2 is 4. Plus 1 times root 3 is root 3. 2 times 2 is 4. So it's nice in this question we get the same denominator of 4, so we can add the numerators together. Now with this, you have to remember all the way back to unit 3, where we dealt with radicals. So how do we add 2 plus root 3 together? And the truth is we can't, right? Because they're not the same radical. So our final answer is 2 plus root 3 over 4. Now, if we take a second and go back and use our calculator, if we type this in sine 45 times cos 45 plus sine 30 times cos 30, we get a decimal of 0.93301. So 0.93301 and so on. Now, what if I type this into my calculator? So in brackets, 2 plus root 3, because I want to add those together first, divided by 4. And we get the exact same decimal. That's why they're special angles, because I can take something that should be as a decimal and create it as a fraction, give it an exact value. And that's what makes these angles so special. Question 2, determine the exact value of cos 45 squared. Now when you square these, you see the exponent 2 is with the cos, it's not with the 45. That just means that you're squaring it. So cos squared and tan squared. So the cos of 45, root 2 over 2, squared, minus tan 60 is root 3, squared. So we have root 2 over 2 times itself. We've already done that up here in question 1. Root 2 over 2 times root 2 over 2, we got 2 over 4. So 2 over 4 minus root 3 squared. Root 3 times root 3 is root 9. Square root of 9 is 3. And then 2 over 4 in lowest terms, of course, a half. So we end up with 1/2 minus 3. Would be negative 2.5. And there's our exact value. Moving on to question 3. What if I go back to a scrap sheet of paper? What if I gave you the question 2x equals 1? And I asked you to solve for x. Well, everybody knows you divide both sides by 2, and x equals 1/2. Pretty straightforward. We're going to do the exact same process for question 3. 2 sine theta equals 1, and I want to determine theta. So I'm going to treat sine theta as if it was just an x. Treat it as a variable, and I want to get that variable by itself. So to do that, I'm going to divide both sides by 2. So that sine theta is equal to 1/2. And if I go up to my table, I can see that sine theta is 30 degrees. Same thing for question B. I want to get tan theta by itself, right? Treat it as a variable. So I'm going to bring the negative 2 over to the other side. So 3 root 3, tan theta equals 3. Divide both sides by 3 root 3. So those cancel out. And now tan theta is 3 over 3 root 3. And with the 3 on top and the 3 on the bottom, these 3's can cancel. So tan theta equals 1 over root 3, which we realize we need to rationalize that. So we multiply that by root 3 over root 3. Tan theta equals root 3 over 3, which means that my angle is 30 degrees. And we'll finish off with a word problem. Person standing 15 meters in front of a flagpole is attempting to determine the exact height. Again, exact height, special angles. So we'll draw ourselves a sketch. Flagpole touching the ground will always be a right angle. Want to determine the height of the pole. The angle from the ground to the top is 30. And they're 15 meters in front. Now, sometimes students ask me, well, what if it's not 30? What if it's like 40 degrees or 50 degrees? Well, if it's 40 or 50 degrees, you can't determine the exact height. It's not possible. So it has to be 30, 45, or 60 in order to get an exact value. So there will never be a question that will ask you for the exact height or the exact anything with an angle that's not 30, 45, or 60. So if this question I have opposite, I have adjacent. So I'm going to do the tan of 30, opposite, adjacent. Again, just like I would any other SOHCAHTOA type question, I'm going to rearrange this by cross multiplying. So H equals tan 30 times 15. Now, normally what we would do is we go to our calculator, type in tan 30 and get our decimal. Of course, we don't want that. We want the exact value. So in place of tan 30, I'm subbing in root 3 over 3. Times 15. So can multiply those together. And we get 15 root 3 over 3. And again, this can be simplified, right? Because I have 15 and 3. 3 divides into 15 5 times. So now h is equal to 5 root 3 meters. So little therefore statement, therefore the exact height of the pole is 5 root 3 meters. And that is our lesson on special angles. Sine, cos, and tan of 30, 45, and 60. When you do the questions, you're simply taking the fractions from this table, subbing it in for a specific angle, and then solving from there to get an exact value. Okay, only 4 questions, 4, 7, 8, and 9.